Good. All righty. So, what I hope to cover today is a little bit of technical aspects of defibrillators, but from a perspective that is relevant to doctors, like what's inside the can, what it takes to sense cardiac electrical signals, although I know you reviewed that with Dr. Strick in the pacemaker session. A little bit on my general concepts of arrhythmia detection and discriminating VT from SVT. I know that Dr. Pillow has talked to you about this, and the Bordeaux group is probably the leading group in the world on analyzing this stuff, but I contribute a little here and there, so you'll just get a little different perspective. A little bit about the components of defibrillator leads and identifying lead failure and its mechanisms. And then if we have time, something about the waveforms that come out of defibrillators, what the electrical shocks, are actually look like. So to begin, right, when we think about what's inside the can of an implantable defibrillator, right, we have a battery, we have circuitry that takes energy from the battery at low voltage and charges up the capacitors when you have to deliver a shock to a high voltage. And the storage capacitors are where energy is stored at a high voltage. And then we have some output circuitry to direct the shock to the leads, which go to the patient. So that's the high level concept. And then, of course, for Hamad, who might be interested in mechanics and mechanical engineering, the packaging challenge of fitting all this into a small titanium can and designing components that'll all fit together is real. And mechanical engineers work on this a lot when we say these are all the circuits and components we need to put in a device, and then just like the guys who package satellites, they're engineers who work on packaging these devices. So now that we've gotten this far, I have a question for the students or your fellow. If the goal here is to deliver high voltage shocks, why don't we we want to make the can as small as possible to implant it, why don't we just charge up the shock capacitor, store the energy in there, put it in the can, and forget about the battery, so we could either have more shocks or run or build a smaller device? What do you think? And while we're putting you on the spot about that, and why don't I put Amaz on the spot about this, because he's actually probably seen some of these things. Let me just tell you this. To quote America's first ambassador to France, my goal here is not to embarrass you. It's to make you think. There are no right and wrong answers. I just care that you have a little skin in the game, as we say, engage with the questions. And, Franklin, who was a wise man, reminded us that when I just lecture at you over a satellite, there's one level of learning, but we get you involved and all of a sudden you start to remember things. But I also want to tell you that I don't bite. I'm not one of those stern European professors. We have a different style in California. So just pretend it's a day at one of our beaches and enjoy the talk. All right. So why don't, Amaz, what do you think? And you can say, I don't know, I've never thought about that. But at least you've thought about it now, right? You can ask for a lifeline. It's a good question, right? You can ask an engineer. Hamad?
Well, you came to the right lecture.
So there are a couple of reasons for this. one important reason that I want to focus on, though, is energy density. Batteries store the energy density of the lithium batteries we use is roughly 3,500 joules per cc. The energy density of a storage capacitor, depending on the technology, is roughly 3 to 5 joules per cc. So we obviously can store hugely more energy at low voltage than we can in a capacitor. And that's one reason we don't. A second reason we don't is that defibrillators are operated by all types of controlling circuits. And especially if we also want to do pacing, right? We want to be able to deliver low voltage pacing pulses efficiently. And so we need low voltage circuitry. And a third part, which I'm not going to spend much time on, is that most capacity, what we'll come to later, is that you can't hold energy indefinitely in a capacitor, whereas batteries can last a very long time. So that's the reason the system's designed that way. It's not that people are too dumb to just store the energy in high voltage places and leave it there. So now one of the things we care about is having devices that last for a long time. And different companies' devices, it turns out, depending on how much battery they have and various other features, last longer or shorter times. And this is somewhat older data, but it makes the point that we really do care about having devices, right, that last 10 years or more, ideally, and that we'd like to understand what that will take. Well, it's obvious once you think about it. The first is, the more battery capacity you have, right, the more battery energy you can use. And device companies vary between ones that have batteries that are in the range of about 1 ampere hour. That means it can deliver a full ampere of current for an hour, to about 2 ampere hours. A second is how much power you actually use when you're not delivering shocks, right? I mean, just to operate the device, how much your circuitry consumes. And one of the things that can sometimes contribute to battery drain is various monitoring features, or for example, in a patient who's developed chronic atrial fibrillation, long-standing persistent atrial fibrillation after an implant, you really need to keep the atrial channel on and monitor it. So you can actually may have some influence here by identifying features that you might not need to conserve energy and removing them. And there are various ways to estimate that. And there's a wonderful paper by a brilliant Irish electrophysiologist, Ernest Lau, on that subject a few years ago, that shows you how you can figure out how fast your battery is depleted for any given company's device, because you reverse engineered a lot of the technology. And I would recommend that to you if you have a sleepless night, but it's not easy reading. Okay, so what are the desirable properties of a defibrillator battery? Well, I mean, we've talked about one, right? We want a lot of battery capacity. Just to give you an idea, and I haven't looked this up for the iPhone 14, but the iPhone 13 has roughly twice the battery capacity of a implantable defibrillator, and you recharge it every night. Whereas we want these things to last for 10 years, not just monitor and deliver shocks, and we can't recharge them. That's a whole other issue of rechargeable devices and what we could do to change battery technology. But right now, all our battery technology uses lithium anode batteries because lithium is very light, and lithium batteries store a lot of energy. But there are differences among lithium batteries depending on what the cathode chemistry is. And that some cathode chemistries allow us to store a very high energy density. And that's great. It means you can run a pacemaker for a long time, but they're completely useless because when it comes to defibrillating, because you can't take energy out of them rapidly. So we also need a battery component, or at least part of the battery, that allows us to, allows it to deliver energy rapidly to the charging circuits when we need it. And lastly, we want a battery that has some reliable way to tell us when it goes belly up. It's not like we look for our flashlight and we can't turn it on. We say, oh, it's time to change the batteries, right? That's obviously not a good solution for a pacemaker dependent patient. So you probably know this, but replacement indicators for pacemakers, international standard, are supposed to give you 6 months warning, and for defibrillators 3 months warning before they go to what we call end of service performance, which means some of the more optional but not life-sustaining features just don't work anymore. And so different battery chemistries have different replacement indicators, and we should know that for the technology you're using. So for example, if you look at a Boston Scientific battery, the battery voltage is not a reliable indicator of when the battery is going to fail. So that's why they actually count the charge that the battery is delivered over its lifetime and have a little meter that shows that to you. On the other hand, if you have a battery chemistry from one of the other manufacturers, it's typically a mix of a chemistry that can deliver high current flows and one with a very high current density. And so this combination of carbon monofluoride, which has a high current flow, a high current density, and silver vanadium oxide, which allows for high current flows, will give you a battery voltage. And this company is telling you the recommended replacement voltage is a certain voltage. So in this case, the voltage on the battery is a reliable measure of when we should replace the battery. Okay, just a bit about the transformer circuits. This is to remind you what these things do. There are circuits inside the battery, inside the device that, I'm sorry, do you hear feedback on my talk or is it okay?
Okay, it's okay.
Okay, all right, good. 'Cause I hear the line.
Is it annoying for you?
Yeah, but I
Okay.
mean, I've been annoyed before. I mean,
No, we try. You can go on, and we try to fix it for you.
Okay, great. No, I have one of these minds that like gets confused when there's too much input. Okay. Just a key point about how does this actually work? If you go out to the local power station, or your neighborhood power transformer station, you probably see these really high voltage lines coming into your community, and then there are wires coming out of that are distributed to your house at lower voltage. And the key point is it's efficient to store energy as direct current energy, and we deliver shocks, which is direct current energy, but we need a system to transform it into alternating current, as I'm sure Amaz knows, to change the voltage. So these things have little iron cores, and the iron ceramic transformers are very important for oscillate at frequencies of 20 to 30,000 times a second. And as they do so, they generate AC current, and that's what allows you to charge a transformer. Just to give you an idea, a transvenous defibrillator stores about 40 joules of energy at 800 or 900 volts in about 10 seconds. and subcutaneous defibrillators store 80 joules of energy at close to 1400 volts in something like 15 to 20 seconds. And of course, the transformers are not 100% efficient, so they have to suck out, 25 to 40% more energy out of your battery than that. So that is a lot of current flow going through the circuits. These circuits don't have to be as strong as the strong circuits in your house, as the circuits that, power your house, but pretty close. They're in that range. All righty, here, let me just go on for a minute. And then we'll get to a few questions. The capacitors. What's important to know about capacitors? Well, you probably remember this. The way a capacitor stores energy is different from a battery. There are two conductors and there's an insulator in between. We call that the dielectric. And the simplest capacitors were two plates with some insulator in between. And the amount of energy stored depends on how high we can charge the voltage. And that depends on how good an insulator it is, because if you put enough voltage through any insulator, it'll eventually break down. And what the surface area is. The surface area determines how much charge you can distribute. And so what we measure is the dielectric constant. That's how strong the insulator is. And of course, how thick the dielectric is. But our goal is to get lots of surface area and a powerful or a strong dielectric, but have very little surface area, very little thickness, because the more thickness we have, that makes the device thicker, and nobody wants that. So for example, the original capacitors we used were actually aluminum foil capacitors. This is the same stuff you have in the kitchen, except it's very thin. And then to get more surface area, it's etched. And then because these etching to make these little, you see in the scanning electron micrograph, little divots isn't enough. They also go through a process called sintering to increase the surface area a lot. So this is one of these like fractal geometry things. So there's a lot of work that goes into making a lot of surface area to store charge in devices. Another approach is just to have a little powder and take all the surface areas of all the little parts of powder. And tantalum powder, which is what Medtronic devices use, is considerably more stronger dielectric than aluminum, but tantalum is a lot heavier because its atomic weight is heavier. All right, I am not going to quiz you on any of that, maybe later, but I want to turn to the process of sensing. And I want to be very specific. The definition of sensing that I use is that it's the process by which defibrillators or pacemakers determine the timing of each actual atrial and ventricular depolarization from the electrograms. So how does this actually work? Well, I think Dr. Strick probably went through this with you, but we have what's called a sensing threshold. So the device waits until the electrical signal exceeds this sensing threshold, and then it puts down a timing marker. And that is what we refer to as a sensed event. Here we can see that the R wave is sensed correctly or appropriately, as that's the jargon we use. Here, if we set the sensing threshold higher, at a greater value than the R wave amplitude, we don't sense the R wave. We refer to this as undersensing. This is a sensing threshold that's set too high. Here, you can see that the sensing threshold will sense the R wave when it's set at a millivolt, but it will also sense the T wave and other potentially small signals. So here, when we sense signals that are undesired, we call this oversensing. Additionally, there are two classes of sensing thresholds. There are fixed sensing thresholds where we just set a constant value for sensing, and that's used in many older pacemakers. And here we see an example of the onset of ventricular fibrillation with quite a bit of undersensing. Alternatively, all implantable defibrillators and many modern pacemakers use some form of dynamic or time varying sensing. And the way this works in principle is that the sensing threshold increases after each sensed or paced event. And then the sensing threshold decreases over time afterwards if there is no sensed event. And so this helps us avoid T waves, but if ventricular fibrillation starts and it misses one fibrillatory wave, it will find the next one. So for example, here it senses this VF electrogram or VT electrogram. It senses this one here, but if it starts to miss, like over here, it will continue to become more sensitive until it picks something up. So those are the key concepts of the sensing process. Now, I know from Dr. Pelot's talk, you have already seen a lot of electrograms, but I just want to give you my take on how to analyze them. When you look at an electrogram, the first question is, what are the channels recorded? What leads in the heart are we showing? And here we show a right ventricular sensing lead, sensing channel, and we show the shock channel between the two shock electrodes. And we show a marker channel. The marker channel identifies sensed events. Devices, as long as the telemetry is working correctly, will deploy a marker for each sensed event and usually put some timing interval on it and maybe even label a classification like what type of detection zone it puts it in. Here, these events are in the ventricular fibrillation zone. And here, and your first job as a clinician is to confirm that there's one sensed event for each actual true cardiac electrogram. We would call that appropriate sensing, which means that there's the number of markers equals the number of ventricular polarizations. Oversensing occurs or is identified by the fact there are more markers than there are real cardiac depolarizations, ventricular depolarizations. Here we see dual chamber markers, right, an atrial channel and ventricular channel, but I'm only showing you the ventricular sensing electrogram. And here, because the R wave is small, the T waves are large relative to the R wave, and they are oversensed. And so we have markers that correspond to both the R wave and the T wave. In fact, the defibrillator, this one, is smart enough to realize their T waves and ignore them at a later stage. But in principle, I just write, for now, I want you to focus on the fact that more markers than cardiac events is oversensing, and conversely, undersensing, right, is more true cardiac electrograms than markers. All right. Does anyone have a question about that this slide? I think this is one of the most important points I want you to learn. All right, silence means either there are no questions or everyone's asleep because I can't really see on my screen here. So let's see if everyone's asleep. Let me try and differentiate between those two possibilities, the same way you could do good differential diagnoses. This is a pacemaker with a fixed sensing threshold of 2 millivolts. We can see that here we have an atrial channel. but I'm talking about the ventricular channel, and this is the ventricular sensing channel. And here's the ventricular signal. So the first question for Yana, is this sensing appropriate? Or is this undersensing or oversensing? And then whatever you tell me, I'm going to ask you, how do you know? Can you folks hear me? Can I get a sign of life from Bordeaux?
Il faut que vous
Okay, good. You
allumiez
can hear
le
me. All right, so you
micro.
get to think, and if you don't know, you can ask one of your colleagues for help. Struggle with it for a minute. Is this appropriate sensing? I mean, this is the first thing you're going to want to know when you look at a tracing. Is the device actually sensing the heart rate or not before you can make sense out of what it's doing?
Yeah, I don't know, but I think there is a problem in the third complex, I mean.
Well, the first question is, what's my rule? Instead of focusing on that, what's my rule about telling appropriate sensing and inappropriate sensing? Which channels are you supposed to compare? Anyone want to help?
Yeah. Hugo Pierre, are you there? We've got a Canadian fellow. I think he's going to be in capacity to answer. What do you think, Hugo Pierre?
Yeah, sorry, what was the last question?
What do you think?
Yes, I'm glad. Thanks for joining. Yes.
He was sleeping, actually.
He was maybe a bit sleepy, but
this
he's
is
Canadian.
No, I'm just kidding you. I'd be asleep at 5 p.m. Believe me, if I had a boring lecture. Look, no, here's
this
the
is
question.
ventricular undersensing.
Yes, and how do you know that?
Because well, we have the markers. And
yes, exactly right. So you have more electrograms and markers, fewer markers than actual cardiac signals, right?
Yes, exactly.
Okay, very good. So this is ventricular undersensing. So now we have another question. Yeah. Why is undersensing occurring? And let me rephrase, let me be a little more specific. We see a 2 millivolt threshold. It's easy to understand for those that we haven't gotten to blanking periods, but like some of these electrograms are in blanking periods, so they wouldn't be sensed. And for those of you who speak Abbott, you know, this little marker tells you this is the pacemaker's blanking period, so we can't count what's happened here. But for example, I've marked with asterisks a whole series of electrograms that are clearly not in blanking periods. They're also greater in amplitude than 2 millivolts. The next level question is, why aren't these sensed?
Not sure.
Okay, you're at the right place. So let's develop that concept, right? So the first question we want to ask is, just because I draw on a little sensing threshold and a sensing electrogram, what are the details of the signal that's compared to the sensing threshold? So let's think this through, right? When the signal comes out of the pacing lead, the first thing that happens is that it's amplified. And this amplified signal is what Abbott displays as the ventricular bipolar signal. After the signal is amplified, it's filtered. The purpose of filtering, as you know, a good EP tech like Hamad will tell you, is to remove unwanted signals. For example, remove higher frequency signals such as electromagnetic interference or lower frequency signals like T waves. And this signal is then taken and rectified. We don't actually know, depending on the company, either this signal may be sent out to your programmer Or this, what we call the narrow band filtered signal. The others call the wide band or unfiltered signal. And some companies may send both, some companies may send one. And then just so you know the rest, which is not important for your clinical work, is that the signal is then what we call rectified. That means anything that's negative is turned into a positive signal. And the reason for that is just simple engineering simplicity, that now we only need one pacing threshold, right? We don't need a positive and a negative threshold to keep attention to, so that we can then take this signal and a circuit that just takes the absolute value is very simple to throw into your electronics, so that we wait until the signal exceeds the value of the sensing threshold, which may be changing with time, but at any one time it's at a certain value, and that's when we get a sense of it. All right, so in this context, just a little bit more about filtering, right? The frequency of transvenous sinus R waves is in the range of typically 20 to 40 hertz. That's typically considerably above the frequency of T waves, which is down around 2 to 4 hertz. So pacemakers can do a pretty good job filtering sinus R waves from T waves. SICD is a much tougher problem. Well, let me backtrack. And even VF electrograms tend to peak around 20 hertz. So while there is some overlap between VF and T waves, not so much. On the other hand, when you have subacute far field signals have lower frequency content, and we can get to why that is, if you guys want to get, if you folks want to get into that. But they overlap considerably with far field T wave frequencies and VF electrogram frequencies. And one of the reasons early versions of SICD had such difficult problems with T wave oversensing is that based on frequency alone, it's very hard to discriminate ventricular fibrillation. Now that you've seen that, let me show you some examples. Here's some actual filtering I did just to show you. Here's a patient's electrogram and sinus rhythm. And here's where we filter it. Yes, please.
I'm sorry. I'm sorry to interrupt, but I have a question. The signal we can see on the controller is already filtered and amplified and modified, or it's the raw signal from the electrode?
Yeah, so as I said a moment ago, and I'll show you some examples, it depends on the company you're looking at, and you should know which companies show you each. So to be very specific, Medtronic shows you wideband unfiltered signals only. Boston and Biotronic show you only filtered signals. Abbott shows you as options for both. The one they call V bipolar is unfiltered or wideband filtered. There's always a little bit of filtering, but yes. The one they call SenseAmp is narrowband filtered. So I apologize for this industry inconsistency, but this allowed me to make a slide and not show you the other data and get you thinking about whether the electrogram that you are looking at is the one device is using to make decisions. And in Medtronic devices, that's never the case, okay? Unless you can really get under the hood in some way. Does that answer your question? Good question.
Thank you. Thank you. Yes.
Any other questions? Okay. So here's just an example of what happens when you filter a signal. You put a 10 hertz high pass filter in, T waves get a lot smaller, R waves get only a little smaller. Sinus rhythm R waves. 20 hertz high pass filter, R waves are a little smaller, T waves pretty much gone. Polymorphic VT, on the other hand, at 20 hertz, the R waves are down to a quarter the size of the baseline R wave, right? The unfiltered signal. So you really do lose a lot of signal in VF when you filter between 15 and 20 hertz. And that's why, for example, pacemakers, lots of pacemakers filter at 20 hertz or a little above that, but most defibrillators filter between 10 and 20 hertz. And the precise values depend on the company. So here is your sense amp filter, right? So now this is this pacemaker, and I'm displaying both signals for you. And you can see that, you know, based on this, what I just showed you, you know, is no surprise that if we compare the sense amp signals with the pacing threshold that's fixed, you can see they exactly match the sensed events as long as we're not in a blanking period, right? So it's lesson here is you need to know what signal the device is actually analyzing to make sense out of the marker channel. Okay. Moving on, just a little bit about characteristics of near field and far field electrograms. Typically, defibrillators and pacemakers sense on a near field electrogram between either the tip and a dedicated ring electrode. This is called dedicated bipolar sensing because the proximal electrode is dedicated to the sensing circuit, or the tip and the shock electrode. This is called integrated bipolar sensing because the proximal electrode is integrated into the shock circuit. There are also other electrograms you can record, say, between the can and one of the shock channels. These are sometimes called leadless ECG. The key point is if you look at a far field signal, that is one that is, and a far field is a terrible word because it's used to mean two different things in clinical electrophysiology, and you have to interpret it in context, just like some words that have the same sound, but you have to know what people are talking about. And I don't know what those would be in French, but the important point here is you can see this far field signal is a much wider signal because it's a global signal. It gets the entire QRS. And in fact, frequency, a simple way to estimate dominant frequency is how narrow and spiky the signal is. The wider the signal is, the lower the frequency. So far field signals are lower frequency than near field sensing signals. Far field, all SICD has to sense with is a far field signal because, pick your signal, but it, it's not close to the source electrogram in the heart. Another thing that happens as we get progressively as far field signals, as we record progressively farther from the heart, the amplitude of the signal decreases. So say, for example, it's pretty common to have a 10 millivolt R wave if you're recording from the RV endocardium, but sub-Q ICDs are lucky to have 2 or 3 millivolt R waves in sinus rhythm, and implantable loop recorders have very small R waves because they're recording between they're both far field and record between a very short electric dipole. Another thing that determines the amplitude is the distance between, this is called the dipole distance, is the distance between the two poles that we're sensing with. So this is, when you look at electrograms, you should understand they have different characteristics because of the location of their electrodes relative to the source signal in the heart, and because of the distance between the recording electrodes. So
can I ask you just a question?
Please.
We do not have any experience with the new Medtronic ICD, the one which is substernal. What are the characteristics of the signals? The same that subcutaneous or intermediate between endovenous and subcutaneous?
Yes, I intentionally left that out because this is not that's a more advanced talk.
For sure.
But to make sure all of you, I'm sorry, who asked that question?
Pierre, it's just
Pierre,
by
oh
personal
yes,
knowledge.
of course, the expert's expert. Who else would this come from? But as Pierre knows, I've spent a lot of time working on design of the sensing and detection algorithm for that device. So, Pierre, that device, and I apologize, I don't want to exit my slide set to pull up the slides, but that device has two types of electrograms it can sense from. The primary, and so just to explain to everyone else, so our students know what we're talking about. Instead of a device where the electrode sits under the skin, this electrode actually goes just underneath the sternum, but outside the pericardium. The potential hoped for advantage of that device is that it could be used for pacing the heart, even though it is not exactly in contact with the epicardium. It's extrapericardial. The sensing characteristics of that signal, of the sensed of the primary sensing vector, which is between two small ring electrodes. So they're not like shock electrodes they're more like the sensing electrodes in SICD, but they're smaller and closer together, is that it's somewhat intermediate between SICD and between subcutaneous and intracardiac. It's bigger than a subcutaneous, but it is, typically say unfiltered electrograms are typically 3 or 4 millivolts. However, so one of the reasons Medtronic, so I will spend a minute on the concepts here, and then I can show you pictures if we get to the end, if you have any interest. It is Medtronic's, the company said, okay, we can hook up a defibrillator that only has we can basically use a minimally modified version of our transvenous defibrillator and not have to put $20 million into redesigning an entire pulse generator. And so we're going to save money and get something that's an extravascular device. I and others, I don't know how many other consultants, but I told them, if you use the same filtering, you are going to be in for a world of hurt because the signals have different frequency characteristics. And they do use the same filtering. So the filtered signals are much smaller. They're down around 1 millivolt to 1.5 millivolts on a good day. And so when Medtronic shows you these signals and you see them going from 3 millivolts down to 1 millivolt, you should have in your head that the actual signal that is filtered, rectified, and analyzed and compared with a sensing threshold is considerably smaller than the one you're actually looking at. Pierre, I could spend an hour on this subject, but is that good enough for this for this part of the talk, and we could come back to more at the end?
Yes, for sure. Thank you very much.
Okay. Yeah. My pleasure. I mean, this is an area of active work. Okay. So I want to move on, and I want to remind you that while sensing, and I know many doctors, use arrhythmia sensing and detection to mean the same thing, but the reason I use it differently is that even in California, we might wear flip-flops, but we try to keep clear thinking. It helps you separate whether the problem and the issues you're dealing with is identifying individual cardiac electrograms, that's sensing, Or if the device isn't doing what you think it should be doing, is it a problem with the process by which the device analyzes a series of sensed events to classify the rhythm and determine if it should be delivering therapy, and if so, which therapy? In other words, detection deals with putting together a sequence of sensed events and making a conclusion about the cardiac rhythm. Okay. Now, I know from Dr. Pelot's talk, you are all very familiar with this concept that defibrillators identify tachycardias based on their rate or cycle length and the duration, either number of seconds or number of intervals of faster than a certain rate. I'm also know from Dr. Pelot's talk that he spent a number of slides explaining that defibrillators also analyze the rhythm to determine if it's a tachycardia, whether it's really VT or SVT. And then I'm not sure how much time you spent on this, but there are also some devices, more than others, including SICD does a lot of this work, has software that identifies non-cardiac or cardiac signals that you shouldn't sense, like T waves. SICD actually does that before the intervals are counted as rate and duration. Medtronic devices and some Abbott devices do this afterwards. And then if the rhythm is fast enough for long enough, and it's judged not to be SVT and not oversensing, then there's some determination about what therapy is delivered. And if it's ATP in a transvenous device, this therapy is delivered immediately. If it's a shock in a transvenous in any device, then we have a charging period, and that can go on for 10 seconds, right? I mean, 10. So the device after that takes a sneak peek. This is called confirmation, and it's often not very precise, but it takes a sneak peek and say, is the rhythm still fast or did it stop? And if it is, it delivers the shock. Pierre, something new you will see with EV-ICD is that the anti-tachycardia pacing has to be delivered through much higher amplitude pulses than occurs with than we do typically with standard pacing pulses and defibrillators. For that reason, we have to the ATP is delivered actually through the shock capacitors. And you, for the first time, will actually see a delay in therapy delivery between detection and ATP. And you want to say, hey, what's going on in there? It's not a 10-second delay, but it takes a second or two to charge up the shock capacitors to enough voltage to deliver the sequence of ATP. So that's something, Pierre, you'll see differently in EV-ICD. All right. So now programming of defibrillators. I know you guys know, you folks have seen a lot of this. Dr. Pelot spent a lot of time on how to program defibrillators in addition to indications. But I want to kind of give you my simplistic version because there's so many complicated rules. It's hard to remember them all, even though as an apparent expert, I'm supposed to remember them. So the first programming rule, as you know, one of our recent and beloved president says, is don't do stupid. You need to treat life-threatening ventricular arrhythmias. Whatever else you have set up, you can't miss treating life-threatening ventricular arrhythmias. In a TV show that I know made it to Europe, Star Trek, the prime directive, guided the Star Trek Enterprise through generations of its captains. And the prime directive of implantable defibrillators is detect and treat life-threatening ventricular arrhythmias. Now, a secondary and important goal, though, is to minimize shocks that aren't necessary. And that is, of course, because shocks are painful, they cause stress, and people come to medical care because of shocks, and they increase the cost of care. And there may or may not be physiologic adverse effects long-term in terms of, patient, in terms of cardiac function. That's hotly debated, but it's certainly true that shocks are stressful and uncomfortable. So we don't want to shock patients more than is necessary. And so let me boil down my view of how we think about this. The first point is we don't want to treat self-terminating VT. And so we want to program a detection time is long enough to allow VT to stop. And also a secondary benefit is atrial fibrillation, which is fast, is often only fast for enough to qualify for a few seconds. If you wait longer, it won't be fast enough. So so the long duration is kind of a poor man's or SVT-VT discriminator. The second key point is don't treat slower tachycardias that are hemodynamically stable. Really, what we want to say is don't treat hemodynamically stable tachycardias. But one of the failed goals of implantable defibrillator diagnostics is to come up with a metric of hemodynamic stability. There were devices built that had pressure sensors, and but this has not turned out to yet be implemented in a practical way. And so a slower tachycardia is thought to be a surrogate for a hemodynamically better tolerated tachycardia. So in most patients, but not all patients, there are patients where it's critical to treat slower tachycardias. Mostly don't treat slower tachycardias since they're more likely to be SVTs. Obviously, if you can use rules to reject SVT and they work, that's a good thing. And that's all I want to say about SVT-VT discrimination. So, and I know Dr. Pelot talked to you about this as well, but just to give you my very, simplistic view of this, SVT-VT discrimination algorithms are those elements in a defibrillator that explicitly classify tachycardias as VT or SVT. They don't say treat or don't treat based on rate or duration. They actually label the tachycardia, ventricular tachycardia, or supraventricular tachycardia. Now, we've been working at this a very long time, since my son, who is now, my younger son, who is now in law school, was programming devices at a young age. And I've been working at this just as long. These are two papers I wrote in 1994. Our first efforts at this, believe it or not, when I was very young. This described the first systematic efforts to understand how algorithms that discriminated inappropriate therapy of SVT from VT could be designed. Their goal was to prevent inappropriate therapy of SVT. And shortly thereafter, I wrote a paper about the dark side of this, that the risk of these algorithms is withholding or delaying life-saving therapy. These principles apply today as well as they did almost 30 years ago. What's different is that the quality of the products has improved a lot, in no small measure to analysis and pushing from work done at in Bordeaux by your mentors. So what are the basic concepts behind SVT-VT discrimination? Well, I'd like you to think about it the way you learned about how to discriminate VT from SVT on a 12-lead ECG. And each of you who've gone through electrocardiography training learned some rules for doing that. And you know how to be an SVT-VT discriminator. But when you look at all these sets of criteria that people talk about, and some of our fellows try and memorize and others just carry in their cell phones. I want to make 3 points. First, they all involve individual rules or discriminators applied in some ordered sequence. It's not just what the rule is, but how you apply them in order that actually makes the difference. The second is most of these discriminators that we use deal with the QRS complex. That means they're single chamber discriminators. Few of them deal with analyzing the atrial electrogram, and that's because during wide complex tachycardias, when the rate is fast, it's sometimes hard to see P waves. So the single chamber rules take priority. And for example, these all deal with things like, well, we'll come to that in a minute. And then finally, most of these single chamber rules analyze something about the shape of the QRS. So for example, is the interval between a positive deflection and a negative deflection more or less than some arbitrary number, right? You know, there are known special shapes that go with that go with SVT and VT, you know, in certain leads. Or here, what is the feature? Is the initial part of it positive or negative? These are all morphological analyses, right? And so when we think about that, that's very similar to what defibrillators do. All defibrillators apply discriminators in an ordered sequence. A difference, and that's why I put this in red, between the way defibrillators work when they're multi-chamber and single chamber is that when there are dual chamber defibrillators, dual chamber rules take priority, and that's different from clinical ECG rules, and we'll come to why that is later. And then finally, just like we do the primary single in surface ECGs, the primary single chamber rule is morphology. So here we see the Boston Scientific diagram, which I like because it's simple. The first thing they do is compare atrial and ventricular rates. And that's a dual chamber rule. Here we have a single chamber rule. And those are the main points. Those are the most important points in this algorithm. Now, what discriminators do we actually use? And I know Dr. Pelot went through this, his own version of this with you. I want to simplify this to my version, which is the primary single chamber discriminator you should use is ventricular electrogram morphology. And you should have some general idea how it works, although different companies do it differently. And the best and most sophisticated analysis and comparison of different morphology algorithms was one published by your institution, your mentors, and they know more about this than just about anybody else. But at a very high level, the reason we like morphology algorithms is they can be used to discriminate any SVT from VT, whereas regularity criteria only reject atrial fibrillation, and abrupt onset or sudden onset criteria only reject sinus tachycardia. And if the onset is abrupt, you obviously, can't reject atrial fibrillation or atrial flutter. Personally, I never apply single chamber onset criteria. You need a priest and a social worker to do that. They're dangerous. And irregularity criteria should be used with caution if you understand the risks. In general, how do morphology algorithms work? The basic principle is the same for all of these. First, the electrogram analyzed is the far field shock electrogram. Second, a snapshot or template is taken of the sinus rhythm electrogram that's stored in the device. Really, the raw waveform isn't stored. What's stored is some reduced shorthand of the features that are extracted, because the amount of computing power, in a device that'll run on a tiny and very little battery over a long, very little power for many, many years is not very great. Modern devices are much better than the early ones we had. The early ones we had probably weren't smart enough to run my refrigerator today. But, the key point is there's not a lot of computing power in implantable devices. When a tachycardia occurs, a snapshot is taken of the tachycardia signal. These tachycardia signals are then compared to the template signal. And if the shape is similar, and we just show you this, the raw waveforms, but in fact, what's being compared are some actual stored, numerical elements. And if that comparison is good enough, and it's typically expressed as some number, that number varies depending on which company's algorithm you're doing. But if the comparison is below a threshold for most of the beats, then we call it VT. And if it's above the threshold for a few of the beats, we call it SVT. So I've been at this for an hour. I think it's time to wake you up. Who's feeling brave? D&B, why don't you try this? This is a hypertrophic cardiomyopathy patient with a single chamber ICD. Is this VT or SVT? That's my first question. And how do you know? And if not, you can ask.
Diandine, cette question, elle est pour toi. Est-ce que vous pouvez... Ouais, merci.
I'm sorry, the question is on the slide. Is this VT or SVT? You have the sensing electrogram, you have the shock electrogram in the marker channel. Here's a story, here's an event.
I would say SVT.
Okay, I'll say great answer. Why do you say it's SVT?
If I look at the shape of the QRS and the P wave, and
so let me just stop you for a minute. All right, so that we're all on the same page. Are you looking at the top channel or the bottom channel?
the bottom one.
Okay, good. And the reason you're looking at the bottom channel is we only analyze shape on shock channels. So you are looking at the shape of the QRS. Okay, I'm with you. And you're saying the shape during tachycardia is the same as the shape or very close to the shape during slower rhythm. So you're going to say this is SVT. Was that your analysis? Right, that's your analysis, correct?
Yes.
Okay, good. I like that analysis. Now I have a question. It is similar, but you notice if I draw a line, if I just follow this dotted horizontal line, the amplitude increases during tachycardia. Is that how do we use the amplitude change? How do we use the amplitude change in our interpretation? When the amplitude increases, do we say it makes it more like VT? That's a difference, or do we say amplitude doesn't count?
Can you say it again?
I want you to notice that the amplitude or height of these signals are all higher in tachycardia than during the slower rhythm?
Yes.
When you have a change in height, is that something? I mean, so these signals are in fact different than these signals. The question is, does this difference matter? It's always a good question. What in terms of VT versus SVT? And the answer is you probably never thought about that before. So let me tell you the answer. The answer is, I'm sorry, go ahead. No, say. The answer is you ignore amplitude. It's overall shape that matters. Abrupt changes in rate frequently change the amplitude of ventricular electrograms during SVT, and you should not, and you should ignore amplitude changes, which you did, and you call this SVT. Okay. Now, I do have one more question. Now that we understand that, which single chamber discriminator correctly classified this rhythm as SVT, and why?
The morphology.
Okay, so you got and you got that right, and that is a correct answer, and it's a correct answer because you analyze morphology to make this distinction between VT and SVT. So you realized morphology, any other algorithm that knew how to analyze morphology would get it right. What would the onset algorithm, what would an onset rule say? How do they work? Well, to remind you, they look for an abrupt change in cycle length and say anything with an abrupt change from a very regular rhythm to another very regular, faster rhythm is VT, and they would call it VT here. Stability, interval stability algorithms would say this is a very regular rhythm, it's not atrial fibrillation. They'd say it's VT. And of course, this is a trick question. Atrial versus ventricular rate comparison might or might not get this correct, but that's not a single chamber algorithm. Now, usually what happens at this point is somebody challenges me and says, Chuck, how do you know for sure this wasn't VT? After all, there's septal VTs that can have similar morphology to sinus in a single lead. And I would say that is a very good point, and you can never tell with certainty. But in this particular case, I know because this patient was in the EP lab, and I turned on rapid atrial pacing exactly at this point. And so what we have here is a little bit of PR prolongation as the PR interval stabilizes, and then, one-to-one conduction of my atrial paced rhythm. So in this, so that while God's truth from single chamber defibrillators can sometimes be hard to be certain about, in this case, we can be certain. Any additional questions about this slide? Okay, so Hamad, let's give you this one. Let's see if you've been listening. Same question. We show you a...
Yes, just a second.
Take your time. I'll get a drink so my voice isn't so hoarse.
Maybe I think more witty, but I'm not sure.
Okay. So how would you, what rule would you use? So the next question is, whatever you say, I'm going to ask you, what rule did you use to come down on one side or the other?
Uh, First of all, the onset, but I'm not sure again.
Right, because here we have slow, here it kind of gradually accelerates, and here it's very stable. Okay, so could be one or the other. I mean, this is not sinus tachycardia. I think I'll give you that. But tachycardias could be VT or SVT. So so I think we've excluded sinus tachycardia, we excluded atrial fibrillation, but we have a regular tachycardia. Okay. And what else did you use to make your decision? So I think you gave exactly the right answer. I don't know. Why is I don't know the right answer? I don't know there is the right answer because this is a sensing electrogram. And I would have pushed you a little bit, but to make a decision. And the rule is you never make a morphology or rhythm determination based on a local bipolar ventricular electrogram. Local ventricular bipoles are good for timing analysis. They are very unreliable for VT-SVT discrimination. Okay, let me show you an example of that. This is the atrial channel during that rhythm. This is a sinus beat. These are electrograms, near field electrograms during atrial tachycardia that triggers the onset of ventricular tachycardia with 2-to-1 VA conduction. And no honest human can tell the difference between these electrograms. So we never use a near field sensing signal to make a global decision about VT versus SVT. I'm going to skip that for a moment. Questions? All right, moving on to dual chamber discrimination. And I know Dr. Pelot reviewed this with you. What my simplistic version is, the key point is a comparison of atrial and ventricular rates. On the left side, we have obvious ventricular tachycardia, more true ventricular electrograms than atrial electrograms. And of course, you want to make sure, not just looking at the markers, that these markers are real electrograms. And we see here they are. Every atrial electrograms corresponds to an upgoing atrial marker. Every ventricular electrogram corresponds to a downgoing ventricular marker. Same here, right? On the other side, we have an irregular atrial rhythm, ventricular rhythm. We have one ventricular marker for each ventricular electrogram. We have many atrial markers, atrial electrograms, and many atrial markers. And we also have a morphology algorithm that tells us this matches sinus rhythm. So we don't have any problem, right, identifying this as atrial fibrillation that's conducted. Now, this is the Abbott algorithm for arrhythmia discrimination. And its tree diagram is more complicated, say, than the Boston one I showed you before. But I don't want you to be focused on this because you're not going to be quizzed on it. The key point I want to make is this, that the first thing this device, that all dual chamber devices do, no matter what goes in down here, and this varies from company to company, is either explicitly or implicitly they compare atrial and ventricular rate. If the ventricular rate is faster, therapy is delivered. If the ventricular rate is not faster, more analysis is done. What you should understand from that, from a clinician's perspective, is that the accuracy of identifying atrial electrograms individually, that is atrial sensing, is critical to any dual chamber algorithm. If a dual chamber algorithm is applied with unreliable atrial sensing, it will give you the wrong, and it will make the wrong decision, no matter how many clever guys designed it. So for example, let's ask what your diagnosis is, Yena. What are we looking at? What is the clinical diagnosis in the upper set of the upper tracing up here? You have an atrial channel and a ventricular sensing channel. What rhythm are we looking at? And if you don't know, you can phone a friend in the room. Yupin, you want to give it a shot?
I can take this one if you want.
Oh, okay.
So this is a tracing of atrial fibrillation, and there is undersensing on
Well,
the atrial.
before we get to that, how do you know it's a? Explain to your colleagues how
All right,
they
so
should identify that.
under the atrial channel, we have a very disorganized rhythm with very fast cycles.
Right. So exactly right. We have lots of electrograms, and they're very erratic, right?
Yeah.
Very short intervals. This is what atrial fibrillation looks like. Okay.
And on the ventricular channel, we see that it's irregular.
We have an irregular ventricular channel. And right, so this is conducted atrial fibrillation.
Yeah.
Now, as you also pointed out, however, this is and the reason you could tell this is atrial undersensing is from what? By analyzing which channel?
The marker channel.
Exactly right. That's how we tell. And there's more markers for the ventricle. And those markers go with every electrogram. But there are many atrial electrograms and a paucity of atrial markers. So this is atrial undersensing, right? So the defibrillator will conclude that this is what rhythm?
So this is for the defibrillator, it's VT.
Right. And it will deliver unnecessary therapies, right? Okay,
Yes.
so it's important for you to be sure that atrial sensing is working correctly. And for example, there are also issues with atrial oversensing that can lead to confusion. And I'm not going to spend time on that. I do want to move on now to defibrillator leads, unless there's questions about SVT-VT discrimination. Okay. So, there are, please.
I have questions. No, not in this part, but just with all these criteria of discrimination, why we still have inappropriate shock? In which point we have to work to, I mean, to have a good algorithm to.
Right. So you're asking an excellent question. What are, another way to rephrase that is, what are the failure modes that are responsible for unnecessary treatments? Broadly speaking, there are two failure modes. Failure mode number one, or let me rephrase that. Failure mode number one is that the discriminator is not applied. We go through all this work in designing these discriminators, but we either turn them off at a certain heart rate, or we turn them off if the patient's been in tachycardia for too long, or the doctor never turned them on. So that's one set of rules for reasons for inappropriate therapies. That never happens in Bordeaux, but it happens in other places. Although rarely you can find very fast heart rates, say 250 beats a minute, that might be faster than you'd want to safely apply an SVT-BT discriminator. The second is that the process of discrimination fails. And as we've just seen, it can fail at one of two levels. Broadly speaking, either there's something about the way the algorithm computes the difference between VT and SVT, that the actual details of the morphology algorithm, or there's a sensing problem that permits reliable determination of the rhythm, such as atrial undersensing or atrial oversensing or ventricular oversensing of T waves. Now, what I haven't satisfied you with exactly what the secret sauce is of where each individual company's proprietary algorithms fail. I could spend time on that, but it's pretty technical, and it will get me, and it will be at a more advanced level than this specific talk. But broadly, those are the classes of failure modes you should think about when unnecessary therapy occurs. Was a discrimination algorithm applied, or was it not even applied? If it was applied, were the sense signals going into the device reliable? If not, then we have to address that point. And if the sense signals were reliable, what is it about the computational aspects of the discriminator that gave a wrong answer? Okay, does that at least point you in the right direction?
Yeah, thank you.
Okay. All right. Implantable defibrillator leads. I want to say something about leads. And I want to introduce this to get the right level of engineering here with a character who appeared on an American comedy show many, many years ago. And Father Guido Sarducci had many funny acts. One of them was what he called the 5-minute university. And he said the 5-minute university was in 5 minutes. He'll teach you what the average college graduate remembers 5 years after graduation. Very good, very low tuition. So I'm going to give you the 5-minute university course on implantable cardioverter defibrillator lead design. The first part is defibrillators have metal conductors, leads, and plastic insulation. The purpose of the metal conductors are to transmit weak bioelectrical signals from the heart to the device, and to transmit higher amplitude pacing and very strong or very high amplitude shock signals from the device to the heart. The purpose of the plastic is to prevent non-cardiac signals from entering the sensing circuit through the big antennas of the metal. So plastic or insulation. Ensure that the signals that come out of the device don't get diffused through the body, right? Actually get delivered to the heart. And then they protect the conductors against corrosion in the unfriendly electrochemical environment of the human body, right? So that's what you want to know about what goes into a lead. Now, if we want to say, how is the plastic and the metal arranged? There are a number of possible arrangements used in various pacing and defibrillator leads. Presently, all implantable defibrillator leads are what we call multi-lumen leads, meaning there's a big block of silicone plastic drilled with a bunch of holes. and through it, metal runs. There are two types of metal conductors. There are cables and there are coils. Why do we have a coil on the lead? We have a coil on the lead because this coil can be used to extend the screw at the tip to fix the lead to the heart. And historically, it's been preferred not to use leads where the screw sticks out all the time. We call that a fixed screw lead as opposed to an extendable screw lead, because the risk of manipulating it inside the atrium and perforation or catching it on chordate tendoni and ripping apart the tricuspid valve and that sort of thing. More recently, we've gone to delivering fixed screw leads through catheters, but presently those are pacing leads, at least in the United States. We'll see more fixed screw defibrillation leads in the future, but for now, the idea is that the coil is used to extend the screw. And it typically has 3 or 4 sub-metal components, and these things are called filars, the components of a coil. And it goes to the screw at the tip. On the other hand, cables are made up of many small filars. 3 or 4 manufacturers use 7x7 blocks of arranged filars. So there are a total of 49 little filars. Most of them are made of a pacing metal called MP35N. This alloy, named because it's 35% nickel and MP for a multiphasic because it has multiple metals in it, was first designed for oil rigs in the Gulf of Mexico because it is corrosion resistant in salt water, fatigue resistant, and is relatively light and strong. It's not a particularly great conductor, but it's good enough for pacing. To allow very high power signals to go through to the heart without using up too much of that energy as heat in the lead. All defibrillation leads have a certain number of filars that are made out of silver. So they typically will have a silver core, a very low resistance conductor. Platinum has also been used inside a MP35N shell. And so the difference between a shock conductor and a shock cable and a pacing cable is not the design of the filars or tensile strength. It's whether they've paid money to like put extra silver metal in there to allow the shock to be transmitted. That's all I want to say about this. Questions about the metallurgy? Good. So now, how do leads break? The metal in leads break by fractures. What causes fractures? Repetitive stress. Now, it turns out, and the mechanical engineer in the audience will know this, that the stress on a stress applied mechanically depends on how much you bend the lead, how much, and you guys folks all know that from bending paper clips, right? You can bend it a little bit a lot of times, but only bend it in half a few times. And stress computationally is inversely proportional to the radius of curvature. That means we can actually compute stress from radiographs, chest x-rays, and that sort of thing. And that's a project I'm actively working on right now. Now, what are the diagnostics we have for when a fracture occurs? Well, the first diagnostic used was impedance. And textbooks for years taught us that impedance increases in conductor fractures. So here, on the other hand, is and here, for example, is what you see in textbooks. Here you see the conductor impedance, and you see an abrupt increase to an open circuit. And we're taught this is the signature of a conductor fracture. However, so I guess the first question we should ask is, what is impedance? And who's our engineer in the room? Is that Hamad? Well, okay. The engineer in the room will tell you, right? If I asked you what is voltage and put you folks to the test, you'd probably be able to tell me voltage is the potential energy of each electron in the circuit, in the battery, or in the shock capacitor. And you'd probably also be able to tell me that current is the number of, as a physical representation, it's the number of electrons, right? It's a measure of the number of electrons that flow by any given point in a certain period of time. And if there's an amount of electrons called a Coulomb that's in the range of 10 to the 19th. And that's the unit we use. It's, big, a lot of electrons. That gives you an amount, and how much flows past a certain point in your circuit. That's what current is. The definition of impedance does not have a physical representation. Impedance is simply the ratio of voltage to current in a circuit. And that's because impedance has two different components. But when we're just dealing with leads and the way it's measured currently, I'm going to dumb it down and say impedance relates to energy dissipated in the lead. And that part of impedance is called resistance. There's also another part of impedance that's highly relevant for alternating currents called reactance, that involved in energy stored in the system. Say if you put your device in an MRI scanner, it can help store energy from the magnetic fields. And that's something we don't want to do, but we're not going to go there. That's for a more advanced course. Now, the problem with this conception is that Dr. Pelot and Dr. Bordachar and Dr. Strick and I have all learned that when patient conductor breaks, they usually present as oversensing, as some type of abnormal signals that have some very specific characteristics. And I know Dr. Pelot showed you one of those during his lecture with a normal impedance, right? Here's one of my leads. And when we took it out, you can see the pacing coil was completely separated. And when we melted away the plastic, the whole thing fell apart. And so, as a curious person, I wanted to know. Well, the first thing I realized, this is not what books tell us happen. How does this happen? Why does this happen, right? And it took me years to design an experiment to understand this, and I'm only going to spend a minute on it, but I do want to spend a minute just to let you know that I'm still doing different stuff. And so, when device companies break leads, they just want some measure of how many times they can bend the thing till it's completely broke. And they write that down as how long that conductor lasted. So they obviously do this on these bending apparatuses, and they do it in air. So they obviously can't record any signals, right? Because you need a conductor around them to record a signal. And they use short conductor segments, right? So they're not hooked up to a lead device. So you don't know what the device electrograms and diagnostics show. That's what we see coming out our end in our world. And they run it till the lead breaks, until the wire breaks. So, you know, they have no idea what's going on when it's partially broke. So after it took a while, but we designed an apparatus that took whole leads and put them in a bending system. And then we connected it to a defibrillator outside this, to a defibrillator. And we continuously telemetered the defibrillator signals to a storage device. And then we waterproofed the whole thing so that we could record electrical signals. So we dumped it in a saline bath and put in a simulated EKG to make it look real, real. And then we recorded these signals, and then we put some very high precision resistance measuring probes on to measure the resistance in the individual conductors, which we dissected out. And then we recorded that about as frequently as we could. And then we set about breaking leads. Who doesn't enjoy taking stuff and smashing it, right? And this turned out to be a lot of work. But the good thing was we could stop this experiment at any point and take the leads off and x-ray them and see whether anything was broke or not, right? So what did we find? Well, I don't want to spend a huge amount of time on this, but I want to just make a few key points. First, for both the coil and the ring, oversensing events and oversensing alerts pretty much always happen before inappropriate shocks. For example, and that happened, and we'll show you some examples of that. Another thing is that impedance alerts usually didn't occur until after inappropriate shocks. So, for example, here we see oversensing, and you just look at your sensing channel, and this is the paste rate, the VS rate, and all of a sudden we have these very fast little intervals, and here's the sensing channel. We can see the abnormal signals here. Same thing over here, right? But when we look at impedance changes, and this is a ring cable, on most of the bending cycles, the peak to trough impedance change is very small, only a few ohms. And even occasionally, it rarely gets to up to 30 ohms. So depending on when you did a single measurement, you might never measure anything, or you might get lucky and measure a 30 ohm change and say, what does that mean? On the other hand, with a conductor coil, we have oversensing that, led to inappropriate therapy. And we have the maximum change in impedance is 4 ohms, which you'd never notice in a pace sense conductor. Now, there is a difference between the way coils and cables break. When a coil breaks, let's start with the cable, it's on top. You can see we can break several filars. These things are super hard to see. And even with high resolution radiographs, photomicrographs, we couldn't see them well. So to be 100% sure, we took them off and did scanning EM, electron micrographs. And you can see here, we got several broken filars, and the actual change between peak and trough impedance here is 0.006 of an ohm. That's because these other conductors are so good, they barely notice that these filars are missing. You only see this much change when the entire conductor is completely fractured, and we can see that. It's hard to see that complete fracture here on the X-ray, but if we do a photomicrograph, you can see this is completely gone. The reason the impedance doesn't go to 3,000 is that all of these cables have an inner insulation around them. And as long as you don't break this inner insulation, it's a lot like the Teflon in your frying pan, very thin and sturdy, you don't get an impedance increase that you can clinically detect. And it's only when you see these impedance increases, that means the ends of the conductor completely separate. Similarly, for a coil, differently for a coil, when you have a partial fracture, you do get oversensing because there are only four filers or 3 filers, depending on the coil we're dealing with. And there's no constraining inner insulation to hold it in place, so they can flex more. And, we also only get, impedance alerts when we have a complete separation. So now we know what it takes to come up with our diagnostics. And I'm not going to spend time on any more of those slides, but I just thought I'd show you, that in California, we do some stuff too. I want to spend a minute on the insulation because you hear about different types of insulation. But broadly speaking, most of the insulation in leads, the body is always silicone. Great thing about silicone, it's very flexible and it's biostable and it's biocompatible. Downside, we'll get to this, it's mechanically weak. The silicone in the heels of your shoes wear out over time. I'm getting ahead of myself here, but we call that abrasion. And it's subject to various types of mechanical deficiencies. The Teflon or Teflon-like polymers, for those of you who really want to know, ETFE and PTFE, and they have long names, and I'm not going to pronounce them. Basically, they keep the cables from unwinding. They keep the cables from cutting into the silicone. They make it easier to build these leads. And then finally, there's often some outer layer that's tougher than the silicone. And ideally, that should be both strong and slippery, because we don't like putting sticky plastic in veins. But we want it to be strong enough that we can't break or cut it, and even better if it were electrocautery resistant. How does insulation fail? One of 2 ways. It either fails from mechanical wear, which is the way silicon fails, either by abrading it, like, as you scuff away your shoes, or deforming it from pressure. This is called cold flow. The tougher plastics degrade by chemical processes, and the details are less important. But the main point is mechanical bending is what breaks conductors, and slow wear and tear is what degrades insulators unless it's a chemical process. Also, insulation breaches usually present, for reasons I'm not going to discuss, with normal pacing impedance. For example, here is an insulation breach in the pocket because the can is rubbing on the silicone lead and abrading it. We see the silicone is completely shredded over the conductor. We see the impedance trend is absolutely normal. So I will stop here for questions. I got done a few minutes early. I brought some slides on shockwave forms that we could discuss, but I've also gone through a lot. You've been sitting for 2 hours. So why don't I see if you have some questions? And this was a sign at Starbucks that I like. If you read it, unattended children will be given an espresso and a free puppy. For those of you who aren't parents, you may have to wait a little while to understand the significance of this, but to make your life hell. But let me stop and let you ask any questions you have.
Yeah, thank you, Chuck. In the last case, you showed with insulation abrasion could be a contact. Yes, the red arrow, for example, there could be a contact between a conductor, one of the conductor, and the can. Will it be influence the impedance measurement in any way, or?
This is so, let me, great question. And, so let me expand. Let me kind of take a moment to expand Dr. Pelot's question for the students. I'm sure you heard it, but to like get at the significance. Dr. Pelot's asking this very obvious, very, logical question. Let's say we strip the plastic off this conductor. That means the conductor should then be able to contact the can. If it comes in contact with the can and you measure the electrical impedance, you should have a very low electrical resistance in there because you have metal on metal conductor. Correct? That's your question.
Yeah.
Right?
Yeah.
Now, what actually happens is that as you abrade this and you put a hole in it, the lead rotates a little here and there. So the actual through and through hole may not be quite this, isn't quite this big. And the through and through hole isn't always pointing exactly at the can. It's pointing at the, it might be pointing, or it might be a few millimeters away from the can, right? As the can moves relative to the body. However, there is always a current pathway that can get to the can that goes through a millimeter or two or so of extracellular fluid, right?
Yeah.
So the question now comes, how close does the contact of the lead need to be with the can to measure an abnormal impedance? And how close does it need to be to get an abnormal electrical signal from where you're picking up, say, signals off the pectoral muscle that will enter the pay-sense circuit through that insulation breach, because that's sitting right on the pectoral muscle. So here's what you need to know. And I know the answer to this, not because God gave it to me, but because I did some experiments and we published this in Heart Rhythm in 2019 about what the actual impedances are in here, depending on how far away. And in fact, let me think. I could pull up this paper if you want. Let me see if I can explain it. Rather than just showing it to you, because I want to get to let other people ask questions. What we did was make an insulation breach and take leads and put them in a saline bath right under the can. And then we separated the lead from the can by a known short distance. How did we do this? Well, if you think about it, and I don't know what you call them in French, but you have these and we have these, and they're these little thin piece of plastic that you can put under your hot cup of coffee to keep your coffee from cup from damaging or staining a good wood table. And now if you can imagine a thin piece of plastic cut down to a fraction of a millimeter, say quarter of a millimeter, half a millimeter, et cetera, and calibrated. So we call these little things shims, and those are what mechanical engineers call separators. We separated the can from the lead, from the insulation breach by shims, and started with 1/4 millimeter, 1/2 millimeter, and that sort of thing. And then we measured impedance. And it turns out that basically to measure an abnormal pacing impedance, you have to have direct metal to metal contact between the can and the lead. And even if you just put the lead on top of the can, it doesn't always become a low impedance, because you have to be, because the lead has some insulation that, because the actual metal is separated by the thickness of the insulation on both sides of the breach. Am I making sense? Maybe I'm not making sense. Let me pull up, this is actually something that's rare that I can teach you guys anything. Let me stop sharing this screen. And let me pull up this paper really quick. And then I will, and I'll show it to you. Give me one sec. It will take me a minute to find it in my classification here. In my okay, so now you should see this paper, right?
Yeah. So
what we did, we cut some big holes in in cables, and in shock cables, and said, much bigger than any reasonable insulation breach. And then let's see if I can enlarge this, and then I will come down here. And then we took these very thin, took these very thin pieces of plastic, put the lead right on top of the can. We knew how thick this plastic was, and we oriented them so the lead was a part of the lead that has the insulation breaches right over the can, and we made breaches of different length. And then we went out there and we measured the shock impedance. And without going through those details, I want to give you this concept that if you have a millimeter of interstitial fluid, that the impedance of interstitial fluid is about 1,000 ohms per millimeter. Whereas and so if you have 1,000 ohm impedance, and so even if you put the lead down right on the can, what actually touches the can, you can see is the plastic right here. Does that make sense? Maybe I can go here. That if we you can see my cursor, right? If we lay this right on the can, what'll actually happen is the plastic touches the can here, the plastic touches the can here. We have a huge insulation breach, but there's a little interstitial fluid between that and the can. So it really has to actually just be bending up against the can. Now, on the other hand, an impedance of 1,000 ohms will definitely allow abnormal signals from myopotentials to get in. Another difference between oversensing metrics and impedance metrics, which Dr. Pelot knows very well, is that oversensing metrics are operating 24/7, right? The sensing channel is working all day and all night. So anytime you move, use your pectoral muscle, those signals will go into the device and be recorded and oversense the atrium and inhibit the pacemaker and be stored. On the other hand, most devices only measure pacing impedance somewhere between once a day and once an hour.
That was my second question. Why they don't they measure impedance every beat? I know also that Biotronic does that, but why not the other manufacturers? Is this energy costly, or
does Medtronic measure it every beat, or do they measure impedance once an hour?
Now, Biotronic, I think it's every beat.
See, that's Dr. Pelot knows the details of each of these companies much better than I do. When I checked with Biotronic and wrote a review, when you and I wrote a review paper together, which you co-authored, by the way, I called up your contacts at Biotronic because
Yeah.
you would know those guys. They told me it's once an hour.
Okay,
So
okay.
you may be right, but that's what they told me. But the answer is yes, it takes a certain amount of energy to run that. And it interferes with sensing to do it. I mean, transiently for, trying, it's only a few hundred milliseconds that it does it. And once an hour is no big deal. But, but one of my, I think I don't think you need to measure impedance every continuously to get a better measurement. I think what you need to do is instead of making just one measurement when you make it, what we did, we measured 60 times, we measured 60 times a second for 5 seconds. And if we do that, or for 7 seconds, roughly that, if we did 500 samples at 65 hertz, so that when you're moving your shoulder around, you can see differences in impedance. And if you have 500 measurements made over, or even in a device, let's say you dumbed it down and add 50 measurements made over 1 second, right? Then you could determine what the variability of that was, and it would be, and you could, and you could you could set your thresholds for abnormal change in impedance to be much more sensitive than we do today.
Yeah. Okay.
Finally, there's one last thing. We all measure shock impedance to an accuracy of plus or minus 1 ohm. There is no company that measures pacing impedance to an accuracy of more than plus or minus 10 ohms. And for example, if you use Medtronic devices, there's a quirk of Medtronic devices where they measure their increments for whatever reason that I don't understand are every 19 ohms. So when you see 2 Medtronic measurements that are close together and look carefully, you might see 519 and 538. And you'd say, how does it get those numbers? That's because it only has 2 choices. Anything in one, it's one or the other, right? It only gives those funny numbers. So it's multiples of, it wouldn't be exactly that. They'd be multiples of 19, but you get the general concept. Okay, so that's what I can say on that subject. Any other questions?
I have a question, Dr. Swerdlow.
Please. Who is this?
I'm a big fan of left bundle branch area pacing, where we screw a pacing lead deep in the septum. And we're starting to see reports of early conductors fracture, especially with stylet-driven lead, probably because of the stress applied to the lead that penetrates deep in the septum. And I was wondering, lead design speaking, do you think it would be feasible in the future to design a smaller ICD lead and to avoid problem like we've seen with the Fidelis lead, for example, or have we reached a certain limit in lead design, ICD lead design?
Yeah, a really good question. So let me and this is as you pointed out, an area of active research. So let me just share my screen again for a moment. Can you see this different slide set now?
No.
No. Okay, that's bad. Okay, let me try again, Chuck. Share screen. How about now?
Yes.
Okay. So I just happened to give a talk on this question of, right, your question. Can we design better leads, right? Super good question. And hold on for a sec. Let me just see here. These are some of the things that, so this is like a fixed screw, a fixed screw lead that fractured, but here are stylet driven leads that came apart because of the bending there, right? And so the things we want to know the answers to. Sorry, I'm going through this faster than I should. Like if you look down here at this area, right? You know, there is a pretty tight bend right here, right? And so the question is, and if you remember from my talk earlier, you know, the greater the curvature, right, the greater the stress. So the questions are, what are the actual stresses? And there's a Chinese group that has measured the stresses on left bundle area leads. And then, you know, and then my favorite lead design slide, let's see, hold on for a second. My favorite lead design slide is this one. I like it because I stole it from a brilliant Czech electrophysiologist, Mirek Jastrzębski, who I'm sure your mentors know, who tweeted, you know, said, you know, tweeted his own view of, hey, why can't we make better lead designs for left bundle area pacing, right? Including like something to get us deeper into the septum reliably, right? An anode ring that actually makes it into the septum. Markers that tell us how deep we are, and various points. This is not lead design, right? This is Twitter, right? And you know, pretty soon we'll all be banned from Twitter because we said something bad about Elon, right? But between now and then, right? You know, we have these issues, right? Do we want a longer helix? And actually there's some patents on, I mean, you know, or do we want some other method to go in, like some guide wire to put through, right? And, you know, something to put use a removable stylet to poke our way in and that sort of thing. But your point is, what's it going to take to make the lead sturdy enough so that it doesn't come apart? And I can, tell you that in our country we have a physiologic pacing symposium, and this year's one was in Seattle in October, and this was an active area of discussion at that, and I was actually invited to give a talk on this subject, a subject about which I knew absolutely nothing about. But I managed to fake it and, you know, discuss what the issues are. And yes, this is a really important subject. And it's an area of active work by lead designers at each of the major manufacturers. Don't know, I know, and beyond that, I think I'm not sure what else you'd like me to say about that.
Oh, thank you.
Okay. All right. Okay. Yeah, I just happened to have this talk hanging around in handy. Other questions, jokes? What can you guys give me a little feedback? Was this at the right level? Was this too simple for you? I know some of this was a lot simpler than Dr. Plow's talk. And I know it's late in the day there. So, you know, any thoughts you have? Now you're way too kind to say anything critical. Okay, that's perfectly okay. So listen, you folks have a good evening. I'll get on with the rest of my day, and then I will send Dr. Plow our my slide sets. He can distribute them. Sylvain, I'll also include the shock waveform slides I was going to use, and if you think they're useful for next year, it seems that I talk slow enough that I don't get through more slides so that, you know, I can either shorten it and include some of that or we can figure out what to do next year. So you guys take care and thanks again for inviting me.
Thank you very much, Jack.
Thank you.
Thank you
Thank
for
you
your
very
time. Thank you.
Thank you. Thank
Okay.
you.
Have a nice day.
Okay, bye. Okay.
Thanks. Bye-bye.